These people had no insulation, no glass, no furnace. They had earth, wood, and one fire. And they outperformed every modern cabin built before 1980. The reason is not what you think. Outside, -31 degrees Fahrenheit. Inside, 50 to 55 degrees, sustained through the night. Not by luck, not by accident, by design. The year is somewhere between 850 and 20 CE, and somewhere along the coast of what we now call Iceland, or the western shore of Norway, or the outer edge of Greenland, a family of 8 to 12 people is sleeping. Outside, the air is at the bottom of what a human body can survive unprotected. Inside, it is cold, but it is survivable. Comfortably survivable. The structure above them is not a house, in any sense we would recognize today. It has no insulation bats, no vapor barrier, no double-pane windows. In many cases, no windows at all. What it has is a roof made of living earth. A ceiling so low that a grown man cannot fully stand in most of the space. A fire in the center of the room, with no chimney. And walls that begin below the ground. Modern reconstructions, built and studied by archaeologists at sites in Iceland in the 1990s, and re-examined by researchers in Scotland in the 2010s, suggest the interior of a well-maintained Viking longhouse held around 50 to 55 degrees Fahrenheit. That's 10 to 13 Celsius, with a single central fire and the body heat of the occupants. That is not a warm house by our standards. But it is a house that kept a family alive at -31 degrees Fahrenheit outside on a diet of one fire. The modern cabin built in 1975 in Vermont, in Minnesota, in Alberta, struggles to hold 55 degrees at 20 above zero, with a propane furnace running 3 times a night. Something was lost between that longhouse and this cabin. Tonight, we find it. The first thing you need to understand about the Viking longhouse is that it was not primitive engineering that happened to survive. It was deliberate engineering, accumulated over generations in one of the harshest climates on Earth. The people who built these structures had been building them for hundreds of years, iterating in the most unforgiving laboratory that exists, the Nordic winter. What they arrived at was not simple. It was a system made of 4 interlocking strategies, each one reinforcing the others. Remove any one of them, and the system degrades. Copy only one, and you miss the point entirely. The 4 strategies were the sod roof, the low ceiling, the central hearth, and the semi-buried foundation. Not insulation, not R-value, not thermal resistance in the sense we use the term today. Something older, and in many ways more intelligent. Before we go further, it is worth pausing for a moment on the transition that erased this knowledge. Not in one generation, but across 4 or 5. The shift began when building became fast. When the goal of construction moved from, "This structure will outlast my grandchildren," to, "This structure will be ready by spring." Concrete came, dimensional lumber came, fiberglass insulation came, and with them came a new vocabulary of performance, built almost entirely around a single metric. R-value, the thermal resistance of a material, measured as its resistance to conductive heat flow. R-value is real. R-value matters. But R-value measures only one of the 3 ways a building loses and gains heat. Conduction, yes. Radiation, not directly. Convection, not at all. And here is where the comparison between a Viking longhouse and a modern insulated cabin goes completely wrong. Because when Engineers or writers look at a sod roof and calculate its R value. They find something moderate, perhaps R8 to R12 per foot of compressed earth. Not impressive by modern standards. And they conclude, primitive. That conclusion, primitive. That conclusion is the mistake. The sod roof was not insulation in the modern sense. It was a thermal battery, a roof made of living turf, 12 to 18 inches deep, contains an extraordinary amount of thermal mass. Not R value, but heat capacity. The difference is this. R value tells you how fast heat moves through a material under steady conditions. Heat capacity tells you how much energy a material can store before it changes temperature. A foot of compressed sod, with its moisture content, with its root structure, absorbs and releases heat slowly, very slowly. Think of it this way. If you put your hand on a cast iron skillet that has been sitting near a fire for 2 hours, you feel heat that was stored, not heat that is being generated. The skillet is not a furnace. It is a battery. The sod roof absorbed the modest heat of the interior through the day and the evening and released it back slowly through the coldest hours of the night. But there is something more. The sod roof had a feature that no fiberglass bat will ever have. When the temperature outside dropped, snow accumulated on top. And snow is an extraordinary insulator. Fresh snow has an R value of approximately R1 per inch. 12 inches of snow on top of a sod roof adds R12 to the system. At exactly the moment when the cold is most severe, the roof becomes more insulating. The house adapts to the weather. Automatically, for free, without a thermostat. Before you add force, read the flow. The second principle is almost embarrassingly simple, once you see it. A longhouse interior typically measured between 5 and 6 feet at its highest point, the central ridge. Near the walls, even lower. Modern cabins average 8 feet of ceiling height. Many new builds are 9 or 10. Here is the consequence of that difference. Heat rises. This is not a metaphor. This is convection. Warm air is less dense than cold air, if of the portage, away from the people living in the lower half of the room. In a modern 8-foot cabin, on a cold night, the top 2 feet of the room may be 10 to 15 degrees warmer than the floor where you sleep. That heat is not warming anyone. It is sitting at the ceiling, pressing against the roof, and conducting outward. In a longhouse with a 5.5-foot ceiling, there is nowhere for that warm air to go. The column of heated air is compressed into the occupied zone. The people sleep in the warmest part of the house, because the warmest part of the house is all of it. This is not an accident of primitive construction. This is a low-volume thermal strategy that reduces heating demand by 40 to 50% compared to the same floor area with modern ceiling heights. It costs nothing to replicate. It requires only the decision to build lower. The third principle is the one that looks most dangerous from the outside and is the most misunderstood. An open fire in the center of the floor, with a hole in the roof above it. No chimney, no damper, no flue liner. From a modern code perspective, this is a catastrophe. From a thermodynamic perspective, it is elegant. Here is what a central hearth does that a wall-mounted wood stove cannot. It radiates in all directions. A wood stove mounted against a wall radiates outward into the room on 3 sides, but conducts heat directly into the wall behind it. A central hearth, positioned at the geometric center of the space, radiates equally in every direction. The floor around it, equal distances, the people sitting in a ring all receive the same radiative load. And the smoke hole, the opening above the fire, was not a design failure to be patched. It was a stack effect driver. The fire heated the air column directly above it. That column of hot air rose, escaped through the smoke hole, and as it exited, it pulled fresh air in from the low entry tunnel, the passage that was deliberately built below the main floor level. Cold air entered low. Warm air exited high. The fire burned clean. The interior stayed pressurized with a slow flow of conditioned air, and the occupants sat in the middle of a convective loop that the building had been designed to create. This is not primitive fire management. This is passive ventilation by design. The fourth principle, and the one that modern earth-sheltered designers rediscovered in the 1970s, is the semi-buried wall. Most longhouses were sited so that the long walls were partially below grade, 1 to 2 feet of the wall buried in the earth. The reason is simple and precise. At 6 feet of depth, in most temperate and subarctic soils, the ground temperature stabilizes. In Scandinavia, in Iceland, in the northern plains of North America, that stable temperature is approximately 35 to 45 degrees Fahrenheit, 2 to 7 Celsius. Not warm, but not -30. The buried wall is not touching outside air at -31 degrees. It is touching soil at 38 degrees. The conductive loss through that wall is reduced by 70 to 80% compared to an above-grade wall in the same exterior air temperature. And the earth, like the sod roof, has thermal mass. It does not spike. It does not plummet. It holds. The house does not fight the outside temperature. The house uses the planet as a buffer. Here is the critical point, and the one that modern analysis almost always misses. None of these 4 principles works at its full potential alone. The sod roof holds heat, but the heated air would still collect at the ceiling and conduct out. If the ceiling were 8 feet high, the low ceiling captures the warm air column, but it would also trap smoke and carbon monoxide if the central hearth did not create a precise upward draft. The central hearth drives the draft, but the cold air intake at floor level would chill the occupants if the buried walls did not buffer the incoming air temperature. The buried walls moderate the entry temperature, but they would eventually lose to ground frost if the sod roof did not prevent the perimeter soil from freezing around the foundation. They hold each other up. The system earns something greater than the sum of its parts. Archaeologists studying reconstructed longhouses in Iceland in the late 1990s found that, when all 4 elements were present, interior temperature held through the night with minimal fuel addition. When researchers removed the sod and replaced it with thatch alone, fuel consumption doubled by morning. The sod was not decoration. It was load-bearing. Thermally. The 1970s earth-sheltered building movement tried to recover the semi-buried strategy. Some of those houses are still standing today and performing exceptionally. Others failed within 15 years. The difference was almost always one variable: moisture management. The Viking longhouse worked in part because the sod roof and the earthen berm were continuous breathing systems. Water moved through them, evaporated, cycled with the seasons. The 1970s versions wrapped everything in waterproof membranes, without understanding vapor movement, and created condensation traps that rotted the structure from inside. The lesson was not that earth-sheltered design fails. The lesson was that you cannot copy one principle without the others. The house was always a system. Treat it like a collection of parts, and it punishes you. Treat it like a system, and it rewards you. So what do you do with this today? 3 applications, each one viable, each one honest about its limitations. The first is the green roof. Not a rooftop garden, not a cosmetic layer of sedum. A true planted roof with a minimum of 8 inches of growing medium, over a properly waterproofed and root-resistant membrane, over a structure engineered for the load. In cold climates, properly installed green roofs have demonstrated heating energy reductions of 20 to 30% in winter. Through the same mechanism the Vikings used, thermal mass plus snow accumulation, plus the insulating effect of the growing medium. The costs are real. The load is real. Engineering is required. But the physics are proven. The second application is earth-sheltered construction. Built into hillside designs where the north, east, and west walls are partially or fully buried, with the south wall open to solar gain, have been documented to achieve passive house performance levels at 40 to 50% of the construction cost of a heavily insulated above-grade structure. The key is vapor management. What failed in the 1970s has since been resolved by building science. The third is the masonry heater, the direct descendant of the central hearth principle. Not a wood stove, not a fireplace, a masonry heater. Sometimes called a Russian stove, a Kachelofan, or a contraflow heater. Burns a small, intense fire for 2 to 3 hours, stores the heat in several hundred pounds of soapstone, fire brick, or ceramic, and radiates that heat slowly into the room for 12 to 24 hours. 1 fire per day. No overnight burns. No smoldering. Extremely clean combustion. And the thermal mass radiates the way a central hearth does, in all directions, from a single source, at a low, steady temperature that the human body reads as deeply comfortable. A 12-inch log, 30 centimeters, holds heat for 8 to 12 hours in a properly charged masonry core. This is the longhouse hearth, refined by 1,000 years of iteration in Russia, Scandinavia, and Central Europe. It was never forgotten there. It was only forgotten here. Before you build anything, one honest note. There are things the longhouse did that you should not replicate. The open smoke hole, without a damper or flue liner, produced significant indoor air quality problems. Carbon monoxide, particulates, eye and respiratory irritation were chronic in longhouse populations. We know this from skeletal analysis of Viking-era remains. The fire management that worked for them worked because they had no alternative and because they adapted their bodies and behavior to it over generations. You have a chimney liner. Use it. You have a damper. Control the draft mechanically. The masonry heater gives you the thermal mass and the radiation pattern of the longhouse hearth, without the air quality compromise. Take the physics. Leave the smoke. The Viking longhouse did not survive -31 Fahrenheit winters because the people inside were hardier than we are. They survived because the building was engineered to survive with them. Every surface was part of the thermal system. The roof held heat. The ceiling contained it. The hearth distributed it. The ground buffered it. Nothing was passive in the sense of being accidental. Everything was passive in the sense of requiring no external energy source beyond one small fire and the bodies of the people inside. The modern cabin fails at 20, above zero. Not because we lack technology. We have more technology than any builder in human history. It fails because we treat each component of the building as an isolated product, instead of as one part of a system. R15 in the walls, R49 in the ceiling, a propane furnace in the basement, and no relationship between any of them. The Vikings did not have technology. They had thermodynamics, and they understood something that our building codes still do not require. A house is a thermal system, or it is a very expensive tent. The fix was always there. You just couldn't see it.